Hello everyone. Today our topic is large-scale data analysis with Apache Spark. This talk is intended to give a quick intro to the Spark programming model, given an overview of using Apache Spark on priced-in clusters, as well as explore its possible application in the HIP. The outline contains Intro to Data Analysis with Apache Spark, Spark Software Stack, Programming with RDDS, Spark Job Anatomy that is running locally and on a cluster, Princeton Big Data Experience, the real-time analysis pipelines using Spark streaming, machine learning libraries that is analysis examples, and of course summary and possible use cases in the HIP. What is Apache Spark? Apache Spark is a cluster computing platform designed to be fast and general purpose for large-scale data processing. It became a de facto industry standard for data analysis, replacing MapReduce computing engine. MapReduce engine is going to be retired by Cloudera, a major Hadoop distribution provider. Spark does not use the MapReduce as an execution engine, however, it is closely integrated with Hadoop ecosystem and can be run via Yarn, use the Hadoop file formats and HDFS storage. On the other hand, it can be used in a standalone mode on any HPC clusters. Example via Slurm Resource Manager as it is done at Princeton. Spark is best known for its ability to persist large datasets in memory between jobs. Spark is written in Scala, but there are language bindings for Python, Scala, and Java. So this slide describes about the Spark software stack. Spark R available starting Spark is 1.5. You can see Spark SQL structured data, Spark streaming real time, mlib machine learning, graphics, graph processing, Spark core, standalone scheduler, Yarn, and Mesos. Spark core contains the basic functionality of Spark, including components for task scheduling, memory management, fault recovery, interacting with storage system, and more. Spark core is also home to the API that defines resilience distributed data sets, that is RDDS, which are Spark's main programming abstractions. RDDS represents a collection of items distributed across many compute nodes that can be manipulated in parallel. Spark Codes provides many APIs for building and manipulating these collections. Spark SQL is Spark's package for working with structured data. It allows querying data via SQL as well as Apache Hive variant of SQL called the Hive Query Language, that is HQL, and it supports many sources of data including Hive tables, Parquet, and JSONs. Beyond providing a SQL interface to Spark, Spark SQL allows developers to intermix SQL queries with the programmatic data manipulation supported by RDTS in Python, Java, and Scala, all within a single application, thus combining SQL with complex analytics. Spark Streaming Real-Time is a Spark component that enables processing of live streams of data. Examples of data streams include log files generated by production web servers or queues of messages containing status updates posted by users of a web service. Spark Streaming provides an API for manipulating data streams that closely matches the Spark Core's RDD API, making it easy for programmers to line the project and move between applications that manipulate data stored in memory on disk or arriving in real time. Underneath its API, Spark Streaming was designed to provide the same degree of fault tolerance, throughput, and scalability as Spark Core. Now Spark comes with a library containing common machine learning functionality called MLlib. MLlib provides multiple types of machine learning algorithms including classification, regression, clustering, and collaborative filtering, as well as supporting functionalities such as model evaluations and data import. It also provides some lower-level ML primitives, including a generic gradient descent optimization algorithm. All of these methods are designed to scale out across a cluster. GraphX is a library for manipulating graphs. Example, a social network friends graph and performing graph parallel computations like Spark Streaming and Spark SQL. GraphX extends the Spark RDD API, allowing us to create a directed graph with arbitrary properties attached to each vertex and edge. GraphX also provides various operators for manipulating graphs. Example, subgraphs and map vertex, and a library of common graph algorithms. Example, PageRank and triangle counting. Under the hood, Spark is designed to efficiently scale up from one to many thousand of compute nodes. To achieve this while maximizing flexibility, Spark can run over a variety of cluster managers, including Hadoop, Yarn, Apache Mesos, and a simple cluster manager included in Spark itself called a standalone scheduler. Heap use case possibility to run root in distributed way using Spark RDDS. GPFS storage, interconnect, infinity band, NFS, 10G Ethernet, use Slurm on general purpose HPC clusters used on Hadoop clusters. Programming with RDDS1. RDDS is resilient distributed datasets are read-only partitioned collections of objects. Each RDDA is split into partitions which can be computed on different nodes of a cluster. Partitions define the level of parallelism in a Spark app. Important parameter to tune. Create an RDD by loading data into it or parallelizing existing collection of objects. This is a list set. This shows when data has no parent RDD or input file, the number of partitions is set according to the total number of cores or node which run executors on them. And this shows Spark automatically sets the number of partitions according to the number of file systems block the file spans over. For reduced tasks, it is set according to the parent RDD. Programming with RDDS2. Transformation. Operations on RDD that return a new RDD. They do not mutate the old RDD, but rather return a pointer to it. Transformation meaning map func. Return a new distributed dataset form by passing each element of the source through our function func. Filter func. Return a new dataset formed by selecting those elements of the source on which func returns true. Actions. Actions force program to produce some output. Note RDDs are lazily evaluated. Action meaning reduce func. Aggregate the elements of the dataset using a function func, which takes two arguments and returns one. The function should be commutative and associative so that it can be computed correctly in parallel. These three is similar to Pythonic map, filter, and reduce syntax, except operator chaining is allowed in Spark. Lambda functions is used most of the time. Collect. Return all the elements of the dataset as an array at the driver program. This is usually useful after a filter or other operation that returns a sufficiently small subset of data. Lazy evaluation. RDD transformations are not evaluated until an action is called on it. Persistent or caching. Unlike MapReduce, where making an intermediate result obtained on the entire dataset available to all nodes would only be possible by splitting the calculation into multiple MapReduce stages, that's chaining, and performing an intermediate shuffle. The crucial feature for iterative algorithms like, for instance, k-means. Programming with RDDS3. Spark allows to persist datasets in memory as well as memory or disk. PySpark uses SPICL for serializing data. Here is the storage level and here is the meaning of each. Memory only, memory and disk, memory only, SIR, memory and disk, SIR, disk only, memory only, 2, memory and disk to etc. of heap. Anatomy of a Spark app running on a cluster 1. Spark uses master or slave architecture, which one central coordinator, that's driver, and many distributed workers, that is executors. Drivers runs its own Java process. Executor each run their own Java processes. For PyScore, Spark content uses py4j to launch a JVM and create a Java Spark context. Executors are ran in JVMs and Python subprocesses tasks which are launched communicated with them using pipes. For Java Scala JVM languages, Spark Contents gives cluster manager divided into two parts, that is worker node or container. Executor has task, cache, task, work node or container. Executor, cache, task, and task is divided. For Python, the driver program Spark Content py4j launches JVM. Spark Content gives cluster manager separated into two parts, worker node or container, where executor in JVM, cache pipe, subpure, and this is same for both